Hi guys, I'm Kieran McAvoy and welcome back to another video. It's great to have you here. Today we're going to be understanding what eigenvectors and their corresponding eigenvalues are. We'll be using animations to our advantage to fully grasp what we're looking for, and I'm not going to just tell you what they are because it's far more enjoyable to try and understand a reason or a pattern for them to have been discovered in the first place. If you're new here and like me, you like maths and engineering, then feel free to subscribe and stick around. Right, let's get into it. Okay, so before we get into looking for eigenvectors, you need to first be comfortable with understanding matrix multiplication as linear transformations of space. And if you're not too comfortable with that, then I do suggest you go and check out some of my earlier videos in this series. I'll leave links in the description below and some in the info card up in the corner there. The gist of it, however, is that if we have a vector in our coordinate system and we multiply that vector by a linear matrix, it linearly transforms or maps that vector onto another vector in our coordinate system. So what we're going to do now is we're going to transform a bunch of vectors at once using matrix M to see what happens. So try and draw up some observations on what you see. So what did you notice? We know that they're transforming by rotating and scaling so they end up in wherever they end up, but they also seem to be moving away from places. They seem to be avoiding some areas and being attracted to some other areas. Okay, so I'll play it again, but this time try and pick out where these areas are. So what areas did you pick out? Well, you may have picked out these areas as the areas that most of the vectors are being attracted to, and these areas as where the vectors seem to be avoiding. So what can we say about the vectors that were close to these areas to begin with? It seems to be that the vectors that are initially close to these areas don't tend to rotate that much, whilst the other vectors do. Well, this leads us to the question that under our transformation matrix, are there vectors that don't rotate at all, that remain completely in line with their original selves? Well, let's have a look. Okay, so there's one that doesn't seem to be rotating under the transformation. It's scaled up by a factor of 2, and importantly, it's remained on its span, which means, by scaling the vector, is the total space that it can describe. Or in other words, it's all of the vectors on this line. Now there's another area that we need to look at, and as we can see, this vector right here remains on its span too, and is scaled by a half. Now, as you may have guessed by now, these are the eigenvectors of this linear transformation, and the amount that those vectors get scaled by are the eigenvalues of the linear transformation. And as a quick side note, the prefix eigen in the German language means characteristic, and you can sort of understand that these are the characteristic vectors of the linear transformation matrix. But after a quick Google, I found that the word eigen itself in the German language means several things, but my favourite was peculiar. And I think that's a worthy choice of describing these vectors, don't you? I mean, they are pretty peculiar. You know, they don't act at all like the rest of them. Now that we've observed the behaviour of these vectors, that when we transform them, they produce scaled versions of themselves, we can ask that exact question in terms of maths. Is there a vector S such that when we transform it with matrix M, it gives us the same vector S, only scaled by some scalar lambda? And now that we have it in terms of an equation, we can solve it. So let's move it all to one side, and currently we can't do much more since we've only got one term involving a matrix. We can, however, write the scaling that lambda does to S in matrix form. For lambda 0, 0, lambda, we'll scale our vector S in the same way. And this is just lambda multiplying the identity matrix. Now we can factor out our vector s, leaving it in this form. Now the only way that this equation can be satisfied is if s is the zero vector, which is boring, or the determinant of all of this matrix, is 0. So calculating the determinant of our matrix M minus lambda times the identity yields a polynomial in terms of lambda, the order of which depends on the dimensions that the matrix spans. So in this case, it will be a quadratic. Solving this quadratic the normal way you would gives us our values of lambda. These are our eigenvalues, because remember we set it up that we have a vector that is multiplied by our transformation matrix that produces the same vector only scaled by this eigenvalue lambda. So now we can sub those values back into the matrix equation to find their corresponding eigenvectors. So subbing in our first eigenvalue into this equation gives this matrix, which when multiplying our generic eigenvector, which we're looking for, gives the zero vector. And after solving the resulting equations, it reveals that any vector where the x-coordinate is twice what the y-coordinate is an eigenvector. And so a simple choice would be the vector 2, 1. So for our second eigenvalue, we do the same thing. We plug in the eigenvalue into the equation, we multiply our second generic eigenvector, and we reveal that any vector that has a y-coordinate that is minus 3 times the x-coordinate is an eigenvector. So a simple choice would be minus 1, 3. And so they are our eigenvectors and will be scaled by their corresponding eigenvalues under the transformation of our matrix M. So that's it, guys. We've gone through the motivation for discovering eigenvectors and eigenvalues, and we've also discussed how to actually find them. Next time we're going to be talking about some real-world applications of these things. Thank you all very much for joining me. I really hope you enjoyed the video and I hope you got some value out of it. And if you did, be sure to leave it a like. And you can subscribe to my channel to stay involved and keep up to date with any of the new content that I'm delivering. You can also follow me on Instagram at KieronWAMcAvoy for daily posts on whatever I'm getting up to for you guys. Thank you all very much for watching. I will see you all in the next video. Bye bye.